So I said that this technique was used to experimentally determine what the different binding energies or the different ionization energies are for the different states in a multi-electron atom. Another way to say states is to talk about different orbitals. So we can do this directly as long as we have certain type of information. The first is that we need to know the energy of the photon that's incident on our gaseous atom. The second piece of information we need to know is what actually the kinetic energy is of the ejected electron, and that's something we can just measure by measuring its velocity. So we can use an equation to relate the incident energy and the kinetic energy to the ionization energy, or the energy that's required to eject an electron. This should all sound incredibly familiar, like I'm just repeating myself in terms of the photoelectric effect, because essentially that's what I'm doing, and that's one reason we spent so much time and did so many set problems on the photoelectric effect. So what we're saying here is the incident energy, so the energy coming in, is just equal to the minimum energy that's required to eject an electron. When we talked about the photoelectric effect, that was called the work function. In this case, it's called the ionization energy, plus whatever kinetic energy we have left over in the electron. So if we want to solve for ionization energy, we can just rearrange this equation. Our ionization energy is going to be equal to the incident energy coming in minus the kinetic energy of the electron. So let's take a look at the different kinetic energies that would be observed in a spectrum for neon where we had this incident energy here. And it turns out that the first kinetic energy that we would see, or the highest kinetic energy, would be 1232 electron volts. So if that's the case, doing a quick little calculation, what would the ionization energy be for a 2p electron in neon? Yep, 22. So basically all we did was take 1254, subtract 1232, and we got 22 electron volts. We can do the same thing for the other observed kinetic energies. So for example, in the second case, we say that we see 1206 in terms of the kinetic energy. Same sort of subtraction problem. What do we have for the ionization energy of the 2s electron? Good quick math. All right, so 48 electron volts. And let's look at the final kinetic energy that we'd observe in this spectrum, which is 384 electron volts. So what is that third corresponding ionization energy? I couldn't quite hear, but I have a feeling everyone said 870 electron volts. So we can actually kind of visualize what we would see if we were looking at a photoelectron spectrum. And what we would see if we were graphing, for example, increasing kinetic energy, is we would see one line corresponding to each of these energies of electrons that we see coming out. And of course, each of those electrons correspond to an electron coming out of a particular orbital. So in the case of 1232, that is our highest kinetic energy. That means it's our lowest ionization energy. It's the smallest amount of energy it takes to pop an electron out of that orbital. So that's why we see the 2p here. The 2s is 1206. And it makes sense that what we see as the greatest ionization energy, which is also the smallest kinetic energy, is that 1s orbital. Remember, because that 1s orbital is all the way down in terms of, if we're thinking about an energy diagram, we're all the way down here. So we have a huge amount of energy we have to put into the system in order to eject an electron. So what I want to point out when you're kind of looking at these numbers here, what the significance is, look at the huge difference between what the ionization energies are for what we call those valence electrons, those outer shell electrons, versus the ionization energy for the 1s orbital. Those are core electrons there. So we can think about something I mentioned last time, which is when we're thinking about chemistry and what's really interesting in terms of chemical reactions, it's mostly valence electrons we're talking about. Those are the ones that tend to be involved in chemical reactions. It makes a lot of sense when we look at it energetically, because if we think about a 1s core electron, that's going to be held really, really tightly to the nucleus. We see that we have to put this huge energy in to actually get a 1s electron ejected. So it makes a lot of sense that we wouldn't want to pay that energy cost in a normal chemical reaction, and we don't. We very rarely would see these core electrons actually being involved in any type of a reaction.